This is 2.7 infrared spectroscopy. Just 3 main points here. So first, you should be able to explain that the absorption of infrared arises from molecular vibrations. Secondly, demonstrate that you understand that groups of atoms within a molecule absorb infrared radiation at characteristic frequencies. And finally, use infrared spectra to deduce functional groups present given wave number data. So, electromagnetic radiation frequency is measured in hertz and wave number is used for infrared. Wave number is measured in centimetres to the power of -1 and is calculated from wavelength in centimetres, where the wave number is 1 divided by the wavelength. The ground state refers to a molecular vibration which is in the lowest possible energy state. Certain molecules can absorb electromagnetic radiation and be raised above the ground state. However, when a molecule absorbs infrared, which has low energy, the bonds vibrate. So energies in infrared radiation correspond to the energies involved in covalent bond vibrations. So infrared spectroscopy is the study of how infrared radiation interacts with covalent bonds in molecules. The exact frequency of the infrared vibration depends on the nature of the bond that is vibrating. So some covalent bonds respond to infrared radiation more than others, resulting in increased bending or stretching of the covalent bond, which is picked up by the spectrometer. Different bonds in a covalent molecule absorb radiation at different frequencies, which are normally measured as wave numbers, as we've seen 1 over the wavelength, and it's measured in centimetres to the power of -1. So an infrared spectrum has a range from 4,000 to 600 centimetres to the -1. The y-axis is the percentage transmittance, and the dips are referred to as peaks. And some covalent bonds absorb infrared particularly strongly, and the table below shows infrared radiation data for some bonds. So for the carbon to hydrogen bond, it's between 2,850 and 3,000. Carbon-carbon double bond, 1450 to 1650. The C-double bond O carbonyl bond, 1650 to 1800. Carbon to oxygen single bond, 1000 to 1300. The OH in alcohols, from 3200 to 3600. And the OH in carboxylic acids, from 2.5 to 3000. So we have an infrared spectrum for ethanol, which is shown here. And you see percentage transmittance at the side and the y-axis and wave number along the bottom. And you'll also note that it increases from right to left, which is the opposite of what you would draw on a normal graph. So the region about 1300 is known as the fingerprint region, and it contains a number of often overlapping signals which relate to specific bonds, such as the carbon-to-carbon bond and the carbon-to-hydrogen bond in the sample molecule. And the fingerprint region is unique for each pure compound that's analysed, so it can be used for comparisons. And above 1300, it's possible to identify individual signals corresponding to specific bonds, which aids elucidation of the structure of the compound. So in the above spectrum, the broad peak centred at 3400, which is this one, is typical of the OH group in an alcohol. And a carboxylic acid has a peak at 1650 to 1800 due to the presence of the carbonyl bond, and another at 2.5 to 3000 due to the presence of the OH bond.